Actually, I'm going to start out with just spherical conductor, and I'm going to get rid of that part. We'll put the empty cavity in just a moment. I have excess charge on it, so the overall charge will make Q. And just for some sense of size R, that should give really narrow it down. Picture in your head. What do we know about the charges? What do we know about the force on a charge in the middle?
It's 0?
Yes. So if the force in the middle is on any charges in the middle, what does that tell you about the electric field inside?
It's 0?
Yes. And so we have a generalized rule there that the electric field in a conductor inside a conductor in electrostatic equilibrium equals 0. That is an idea that we will explain. And that's going to be true regardless of the shape of it. Inside should be 0. So now if I take my cavity, drop back one more. So what does that tell you about the charges? Well, if I throw a bunch of charges into a solid conductor, what will the charges do? What will the excess charges do?
Go towards the outside.
Yeah. So the charges will reside on the surface. So excess charge resides on surface of a conductor in electrostatic equilibrium. Just this part right here. So if I got a conductor, the excess charge is going to move to a surface. Questions up to here? Or we about to throw a cavity into it? All right, so now I've got a conductor here with a hole, or a cavity. It's not a hole, it's a sphere. Spherical conductor with a cavity. Radius R. And I put excess charge on it. Where is that excess charge going to reside?
In the cavity?
You mean it would go into the empty space? Is that what your intent was?
Maybe.
Okay. I'm going to say no. Because if you congregated all that excess charge, let's say that it's electrons. I got a bunch of electrons thrown into the cavity. They all hate each other, so they're going to still push away from each other.
They'll just go on the outside.
Yeah. Yeah, it's the same situation as it would be right here. Excess charge would congregate on the outside. If the excess charge were protons, in other words, we're missing electrons, guess the electrons will start to get sucked in, leaving positive charges around the rim. Now, I'm going to put a positive charge smack dab in the middle of the cavity. I have excess charge inside as I throw excess charge onto the conductor itself. Where will the excess charge reside now?
Empty space in between the cavity.
No, I basically with the empty space there, you're assuming that it would spark or something?
Yeah.
Yeah, let's assume it's not so excessive that it would do
Just
that.
the inner edge of the cavity.
Anyone else?
Or would it depend on what the charge is? Like if it was negative, if it was electrons, it would, or I guess if it was negative, it would go on the inside wall.
Or,
I guess if there's no situation where, since the protons can't move, it would only be that.
all right, so if that middle charge were, let's just say, the middle charge, 3 coulombs, and the excess charge we had thrown on here was -5 coulombs, what would happen? Are you claiming that all -5 coulombs would be hanging out in that inner surface?
I guess that would make sense. I guess some of them will be there, but
Your gut feeling, how much do you think would be hanging out in the inner surface?
-3 coulombs or.
And the other would be then they would have -2 coulombs on the outside. So I would have -3 coulombs here, -2 coulombs there, so that this total is the excess charge. All right, let's actually show evidence for this using Gauss's law. I know that the electric field inside the conductor is 0, assuming it's static in electrostatic equilibrium. So I throw the excess charges on it, I come back a second later. It's legitimate to assume that for a decent conductor, the charges would be in place within a matter of probably microseconds. So if my electric field inside the conductor is 0, well, I've got my outer rim, I've got the inside right there, I got my +3 coulombs right there. I'm going to create a Gaussian surface that runs along here. We're still talking about spheres, this is a cross section, but I've got this, the green is my Gaussian surface. If my electric field is 0, what is the flux going through the line, through my green surface?
Zero.
I hope so. Since this is the electric field times the area, since the electric field is 0, the flux better be 0. So but I also know, since that's my Gaussian surface there is closed, I also know that the electric flux is equal to the enclosed charge over epsilon sub 0. So if my flux is 0, what does the total charge have to be?
0.
And since I have +3 here inside my cavity, how much has to be here on this outer surface? Or this inner surface?
-3.
Because we need a total charge of 0. And since the excess charge was -5, I have -2 left over, that would have to congregate out here. If I wanted to figure out what is the electric, questions to here, then we'll get into some fancier stuff.
what does electric flux mean exactly again?
It's a measure of, I view it as a measure of how much electric field passes through a surface. Yeah, it's not a density of electric field, it's just. Yeah, if your area increases, the flux increases. Is that sufficient?
So,
Alright. Let's take a look at electric field. I have to give some numbers here. We'll do some numbers. Alright, so I got 3, -3, let's make this distance and that distance, we'll make this 10 centimeters and make this 30 centimeters. I'm gonna pick some point A here, a point B, and a point C. Point A is 7 centimeters away. B will make 25 centimeters away, and C is 45 centimeters away. Well, let's take the easy one first. What if I find the electric field at A, B, and C? What's the electric field at point B, 25 centimeters from the center? Yes, we're inside the conductor. So my electric field at B, 0. All right, at A. Now I've got all sorts of different charges. I got this -5 coulombs of charge outside of point A, and I have 3 coulombs in the very middle of it. I know that if I am inside of a charge, so again, if I have my sphere here filled with charge around the outside, there's no electric field in the middle because of even distribution, any electric field would end up canceling out. So when I'm trying to figure out the electric field at point A, I only care about what's closer to the center. This -3 and -2 coulombs do not have any contribution to the electric field at point A. Therefore, I have spherical symmetry. I can assume point charge, and also I've described it as at the smack dab in the middle, so it is a point charge. So it is, so my electric field at point A, KQ over R squared, R hat, 9 times 10 to the 9th, times Q, which is 3 coulombs, divided by the distance squared, which I said was 7 centimeters, so 0.07 squared. And we get something of R hat. Someone be kind enough.
.51 times 10 to the 12th.
10 to the 12th units.
Newtons over coulomb.
I got 10 to the 10.
I got 5.51. 10 to the 12.
You got 10 to the 12th?
Yes.
You got 10 to the 12th. Is anyone prepared to stand up and say, Patrick, how could you? Or Patrick, are you prepared to stand up and look at them with disdain? Not yet. What'd you get?
To the 5.51 to the 12.
To the 12. Did you do 0.07 squared or 0.7 squared?
Alright, sure.
There we go.
107.
Yeah. Patrick, how could you? Okay, so done. These are not, a 3 coulomb charge is huge. Van der Graaf generator is microcoulombs. So this would be more than 1 million times what a Van der Graaf generator would produce, at least the one we have here. All right, so at point C, again, we have spherical symmetry. I can treat this as a point charge. If I'm treating this as a point charge, what is the charge of it?
-2.
Yes. Those cancel out, I'm left with -2. Or I got 3 there and -5 everywhere else, so it adds up to -2. So 9 times 10 to the 9th. -2 times 10 to the, times 10 to the 0. Over 0.45 squared.
Negative 8.89 times 10 to the 10th. Newtons per coulomb. R.
So we have a magnitude of 8.89 times 10 to the 10th newtons per coulomb, unless there's a Gauss error. I assume other people got the, all right. And the negative R hat indicating it's pointing towards the center. Questions to hear?
How come the electric field at A is a number, but the electric field at B is 0? Shouldn't it be the other way around?
Why is the electric field at B 0? Because if there were, electric field were not 0 in the middle, any excess charge would feel a force and it'd be forced one way or the other. It'd be forced to the middle or forced to the outside. So if it's an electrostatic equilibrium, any forces, any electric field or forces that were felt in the middle would have already pushed charges to the position where it would be 0. That's sort of the electrostatic equilibrium is, we've gotten past that part.
Okay.
I feel like I didn't answer your question. You wanna try again?
Yeah. I thought it would be the other way around since A is at the center.
Since A is,
At the center?
you feel like A should be 0? Recognize that there's nothing in there, there's no
Oh.
charges, this is a hole or
Okay.
a missing middle.
Okay, I forgot. I'm sorry.
Okay. You can't tell from my drawing?
So by all the chart, by it being pointed towards the center, that means if like the electric field is pointing towards the surface, but there isn't actually an electric field in the middle, since it all cancels out.
Right, the electric field would be negative, drops to 0, becomes positive. Which brings us to plotting it. Let's plot it. That sounds like fun. All right, so first for some guide, there's my hole or cavity. This is my conductor. So I did the electric field versus distance. So those are key points there. I know that if I am outside of it, with the spherical symmetry, I can treat it like a point charge. And so I've got a 1 over r squared relationship. It's overall negative. And so my electric field should look something like that. I get to the surface. There's a very quick transition to 0. The electric field stays 0 until I get to the inner surface. And once I get past the inner surface, then I am dealing with a net charge of 3 coulombs at the middle. So again, I have a 1 over r squared relationship, but this time it's positive. And so then it, so whatever the size of that is.
Why does it jump when it gets to the center and then come?
if I'm in the conducting part here, the electric field is 0. I know that once I get to the inside here, spherical symmetry keeps this outer, any charges out here inconsequential to the electric field inside, but I do have this charge smack dab in the middle. That 3 coulomb charge does create its own electric field. That's a 1/r² relationship.
Okay,
Does-
so
That's why it jumps.
the top would be the 3 coulombs, or
The,
the top, right at the center would be our 3 coulomb,
yeah, something,
or whatever. it was.
at the middle would be KQ over some tiny number squared.
Okay.
So it's 3 at the top, and then it gets slightly less, and then it's 0 because it's.
Yeah.
It would go down if the outer sphere wasn't there, or if the conductor wasn't there, and we're just kind of
Right.
cutting it that part out.
Yeah. All right. Let's progress this. Any of you happen to remember the relationship between force and potential energy? Or conservative work and potential energy?
Was work the integral of force times del d x.
Or R, I'm in R for today. So that's generic formula for work. I guess, by definition. If it's conservative work, that would be the conservative force, dot dr. And what is conservative work equal to?
Negative potential.
Very close. You left 2 words off.
Negative change.
All right, if I sort of work backwards